Okay, so now we're going to be discussing about nodal analysis. Now, nodal analysis is one of two important methods that allows us to bypass using KCL and KVL. Because what you'll realize is that using KVL and KCL, we have to define several equations that we have to solve back to back, and it becomes very, very tedious. So instead, we employ shortcut methods that are based on KCL and KVL to solve them faster. One of them is nodal analysis. So nodal analysis is based on KCL, hence the name node. And we want to do a few things with nodes. One, we have to only identify essential nodes. From there, we're able to write current equations in terms of voltage. And equivalently, we could find values for current if it's needed. So there are a few things. First, we need to identify essential node, a reference node. A reference by in terms of circuit means we have some kind of ground. And usually this ground is for solving circuit analysis problems is arbitrary. We just have to pick some kind of reference where we say that's where there is no voltage. Another thing we have to also identify is current direction. Now, the term current direction is a bit misleading because current is a scalar and it cannot have direction. But we define a direction anyways, simply because we want to use KVL and KCL to our advantage. So that's also one more thing we have to utilize. Okay, so first, let's consider how we can use KCL or how we can use nodal analysis. Consider the following problem. Right here, we have 10 volts, and this maybe is 7 volts, some reasonable numbers. Now, here are some unreasonable numbers based on experiments. Let's give you 2 ohms. Maybe this is 10 ohms, and this is 6 ohms. In reality, you wouldn't want this because it would actually burn up. So first, we have to identify the 3 following things. Essential nodes. Remember, essential nodes means that we have a node connected by 3 or more branches. So if we look at this, this is the only essential node that we can see. Therefore, we have this one, which we'll call A. So it would denote VA, voltage at node A. We will also have to identify a reference or a ground. In this case, sometimes it's obvious when they have a conducting line, and this conducting line which we'll denote as ground. Now, just to kind of make that explicitly clear, we can circle it, or we can add this ground symbol to it, just to say this is where 0 volts exists. Lastly, we're going to assign a current direction. Now, the assignment of current direction, if it's not given, is arbitrary. So let's say like this, and like this. Doesn't actually matter. We are trying to figure out some kind of solution to this. Now, what if from here you notice how there might not be, you notice how the question isn't really asked just yet? That's mainly because we always try to ignore the question before we end up solving it, because what ends up happening is sometimes we might have a whole system of equations, but we don't need all the equations. We just need to solve one portion in order to get to our point. So I'm going to put this as kind of like an asterisk problem. This problem is kind of ignored until we need it. So in this case, let's say that we wanted the voltage drop across here. Suppose we call this V2, or sorry, V1. Okay? So from here, we set up our current equations in terms of voltage. So what does that mean? So the definition of current is the difference between high potential and low potential divided over the resistance. So in this case, this is signified by the current direction. So we have 10 volts minus the voltage at node A divided over 2 ohms. Now, based on KCL, it's enter, enter, and leaving. So we have one more equation right here. We have 7 volts minus VA divided all over 6 ohms equal to, well, in this case, now VA is at a higher potential compared to the low potential, which is ground, which is 0 volts. So we have 10 ohms. We have that minus this divided by 10 ohms. Now, luckily, we only have one essential node. We don't actually need to solve for many essential nodes. So now we actually can probably ask the question, what is V1 equal to? Well, I mean, if we take a look at it, V1 looks like it's just the difference between 7 volts and VA. So we can write that V1 is equal to 7 volts minus VA. So based on this, if we were to solve this, we'll be able to get to our answer right away. And this is the good thing about using nodal analysis. We can solve for voltages quickly by identifying nodes. And we don't have to use every single equation. Sometimes solving just one helps us find the answer very quickly. So let us do that. So I'm going to simplify very quickly. So we're going to have 5 plus 7 over 6 equal to VA 1/2 plus 1/6 plus 1/10. And we have VA equals to 5 plus 7 over 6 divided over the parallel equivalent combinations. So let's take a look. So it's going to be 6 times 10, 60, plus 2 times 10, 20, plus 2 times 6, 12, divided all over 2 times 6 times 10, or 120. So VA is going to equal to, so we have 37 divided by 6 divided by 80, 92 divided by 120. To put parentheses so we avoid any confusion. And then this is equal to 37 over 92 times 120 divided by 6, or 37 over 92 times 5, which is 5, and then we have the 3, so we have 185 divided by 92. So VA is roughly 2 volts. And that's how we are able to use nodal analysis to quickly find voltage instead of creating multiple systems of equations and then having to solve for each one individually before we get to our answer. So notice that the advantage of nodal analysis is we use current to define voltage. And then later on, when we're going to cover mesh, we're going to actually use voltage to define current. So thank you.